I'm going to go ahead with the meeting beginning ritual. 起立，面向佛堂，参加先鞠躬，一鞠躬，再鞠躬，三鞠躬，参加各位的传习鞠躬，开班一鞠躬，请坐下。
So, when I throw around terms from that field of physics, people will start to get lost a little bit. Last time I talked about superposition and entanglement. Superposition is when things are both and neither. That you can, in real life, we have like yes or no. In the Tao, we talk about, well, it doesn't have to be yes or no. It can be yes and no. It can be neither, possibility, or both, or something in between, or neither. Those are all possibilities. So that mindset is one of the reasons why physicists find themselves resonating with the Tao. Superposition, entanglement is when what happens to one affects the other instantly. So the question is, how does that make quantum computing more powerful? So it's a simple question, but to answer the question clearly and simply can be a challenge. So the way that I can help everyone understand is to begin with an example about how different ways of solving a problem can be very different, can be very different in the time that it takes and effectiveness. So for my bullet here about the different ways of solving a problem, let me ask everyone to imagine a deck of cards, playing cards, that have been scattered all around. It's on a table. It's really messy. Now, within this mess of cards, there are some special cards that look very similar but are taller. They are taller than regular cards by 1 inch. But because they're all scattered everywhere, you can't really tell. Pardon me. You can't really tell visually which ones are the ones that are taller. So now imagine that you have this robot that's very sophisticated that can do the task of looking through all these cards that are scattered everywhere and find the ones that are taller. Okay. Now you would imagine that the robot would do things in a similar way that computers would do today. That is, the robot will take cards and compare them. If they're the same, oh, okay, well, maybe they're not it. But if one is taller than the other, then the robot will set aside the taller one, the taller card, and that's one of the results that you find. So you realize then that the robot has to go through all the different comparisons one by one. You know, like that, right? So that's going to take a while. Now, imagine that you have an even smarter robot, a robot that has learned how human beings will solve a problem like this. That robot will gather up all the cards, together, and then set them, against the table to even them out, and then look at it. Most of the cards are the same size. And then there's a few cards that are taller. Right away, the tall cards will stand out from the pack, right? Then all that the robot has to do is to pull them out. There's your answer. So that is a dramatically faster solution. I think everyone can see that. It's a lot faster than comparing the cards one by one. So that example doesn't actually have a whole lot to do with quantum computing. It's a way for me to demonstrate how a different approach can be much faster, and when it's much faster, we say that it's more powerful. It's a more powerful way to solve a problem. So it's a similar mindset that causes the quantum computing to be more powerful and faster than conventional computing. And then I talk about how we can use the many worlds interpretation of quantum mechanics to help you see why quantum computing is so different and so weird, so bizarre. So I need to talk about many worlds interpretation. This will take us a little deeper into quantum mechanics. And I put interpretation here in blue because I want to be very exact in the terminology. I have seen a lot of people talk about the many worlds theory. It's not a theory, it's an interpretation. Interpretation, not the same as theory, and I'll explain why they're different. I have to take a roundabout way to explain many worlds. And I begin with this, with cat. Schrodinger's cat. So I think that this is going to be useful to people even when they're not interested in quantum mechanics or physics, because as we go through everyday life, occasionally we hear people say Schrodinger's cat. Now, when the term comes up, I find that people are divided into two camps. Everybody will be like, oh yeah, okay, I've heard of Schrodinger's cat, but then there's a group of people who are not really sure what that term entails, and then there's a small group of people who know exactly what that is. But regardless, everybody is like nodding as if they understood. So today, my goal is to make sure that you understand as well. What do people mean when they bring up the term Schrodinger's cat? When would it be practical or correct for you to use the term yourself? What is Schrodinger's cat? So first, what it is a thought experiment. Dr. Erwin Schrödinger, he's an Austrian, and he devised this thought experiment back in 1935. So at that time, quantum mechanics had already become known. And by the way, quantum mechanics is not a theory either. It's literally a set of mechanics. It's a collection of ways to do calculations to reliably predict results at the quantum level. They work really well. But for the theory that explains it, we still have to wait for the grand unified theory. But back to Schrödinger's cat. So at that time, they already knew that particles can exhibit the wave-particle duality at the subatomic level, that even in the dual slit experiments, they can see how photons can be treated as a particle or as a wave, and both at the same time in neither. So then what he wanted to demonstrate, what Dr. Schrödinger wanted to demonstrate, was that it's not just for photons and electrons and particles, that duality, the quantum duality, can extend all the way into what we can perceive, into affecting objects and living things at the human level. So he suggests an experiment that looks like this in a closed space, like a vault or an enclosure that there's no sound transmission, so you can't put your ear up to it and hear meow, and then you say, oh, the cat is alive. Okay, so this is something that's completely soundproof. You can't look into it at all. And that's why they sometimes say it's a vault. And you have you have a source of radioactivity. This is a radioactive isotope. So if it decays, and there's a 50% chance that it will decay, if it decays, it will trigger a lever that causes this hammer to fall on poison, and the poison will kill the cat. So what it's saying, this is a fancy way to say that you have a mechanism here that produces a 50-50 chance of the cat being alive or dead. That's why you see the drawing of a dead cat and the drawing of a cat that's alive superimposed onto one another. The cat is now in superposition. So that's what superposition means. Of the two possible states, the cat can be both simultaneously. So when you open up the vault, when you open up this enclosure and you make an observation, here, kitty, kitty, then you see if the cat is alive or dead. The observation will collapse the superposition into one or two possible states, alive or dead. So far, this is just a fancy way of saying that, well, you don't know if the cat is dead or not until you open it up. That makes common sense to me. Okay, I can understand that. So I hope they don't hand out Nobel Prizes just for something like this. You know, I could have told you that. I could have said, well, you don't know if the cat is alive or dead. Now give me the Nobel Prize, right? So what physicists think about is that before you actually make the observation, is the cat alive or dead? Common sense would tell you that, well, maybe dead, maybe alive. I don't really know, but it's one or the other. And physicists will say, no, it's actually both. Both dead and alive. That's the problem. That's the weirdness. That's the quantum weirdness. Okay, so how do we interpret that? How do we interpret the state of the cat, the Schrodinger's cat? Superposition ends when observation takes place, when you open it up. And hear the cat go, meow, okay, it's alive. Observation is the same as measurement. That is, you are looking into it, you see what it is. The technical term, they'll say that this is collapsing the wave function of probabilistic states into one state, into one or the other. So observation, in this case, has a whole lot to do with it. Here you see a cartoon for Schrodinger's cat. Is it alive or dead? Well, it's purposely written in this graphical design so that you can see alive and you can see dead. Okay, so, and then some physicists will say that, well, I don't like observer because I think that the world continues on even when it's not observed. It's like a Zen koan that says if a tree falls in the forest but there's nobody else around to hear it, is it really making a sound? You know, if there's no observer, what then? Reality should proceed exactly as it was before. So what if there's no observation? And so there's an alternative interpretation called many worlds. So in the many worlds interpretation, literally the universe diverges into two, one where the cat lives, the other one where the cat dies. So the technical term, the two are decoherent from each other, which just means that there's no way for the two universes to communicate back and forth. They're decoherent, they're separate, they're isolated from one another. And when you open up the box, you become entangled with the cat, which is that if the cat is dead, you're in the universe where the cat is dead, you become entangled with that, therefore you observe, therefore you see the dead cat. If you are in the other universe, then you become entangled with the alive cat, and therefore you see that. So the difference between the two is that whether you observe or not, there are two universes that coexist, and they're both very real. And then back to Copenhagen interpretation, no, there's no multiple universes, there's just the one universe, and that's why you can communicate across different universes, etc. So the interpretation is not theory, it's a way to help you see what the theory is saying. So, and you begin to see why people lose their minds when they talk about stuff like this. Schrodinger's cat. Now you begin to see what I'm getting at. So it's all really bizarre. Wanted, dead and alive. Schrodinger's cat. Okay, now to tie it together with quantum computing, if I have 2 bits, and the 2 bits can be 1 or 0, then I have 4 possibilities, 0, 0, 1, 1, 0, 1, 1, 0. So those are the 4 states. In quantum computing, these are qubits, which means that 0, 0, 0, 1, 1, 0, 1, 1, they will simultaneously exist in the qubits. If I increase the number of qubits, I get more possible simultaneous states. Here, when I say bits, I mean qubits. So right now, the maximum is 12 qubits entangled together, and that's just 4,096 states. Now, before you read the rest of it, let me explain. When I'm doing a calculation, and the application that quantum computing is really good at is factoring numbers, factoring primes, and if I were to calculate with just a computer, I write a simple algorithm. I'm trying one number after another. I'm like the robot trying to compare the different cards together, one after another. Now, just imagine that when I'm doing these calculations, I have a whole bunch of versions of me in different universes all carrying out the same computation at the same time. but each one for a different possible states out of the 4096, as an example. So 4096 versions of me, each one handling one of the states, one of the 4096. So I have accelerated my computation by a factor of 4,000 because by the time I'm done with one number, my 4,000 brothers across the multiverse, they're done with theirs, and somebody has come back with a result. So they don't. So in quantum computing, and this is where quantum physicists will say, well, there's not really those multiverses out there, but the quantum computer will work as if there are. So the magic is that it's coming back with a result as if it's got many, many versions of itself all computing the same problem at the same time. So that's the mind-blowing part about quantum computing, and it's all hinged upon superposition and entanglement. Now you see what I mean. Now, when I have only 4,096 computing problems being executed in parallel, I can still simulate that with a very fast computer conventionally. So it's going to come back with a result in maybe like a couple of seconds for a particular problem. That's fine. But I talked about quantum supremacy. That's when you get to 50 bits. Then you've got this many possibility simultaneous states that all exist at the same time. At that point, it becomes impossible to simulate with conventional computing. In fact, quantum computing at that point will far outstrip the ability of conventional computers at factoring large numbers. And the significance of that is that all of our encryption schemes on the internet today is dependent on that. If somebody creates a quantum computer with 50 qubits, that person can crack absolutely every encryption scheme that we have today without breaking sweat before breakfast. That's why people are racing to see how many more qubits they can entangle in a state of stability that can be used for computing. So it's not important to know all the details. The more important thing is for me to get everyone to get the feel for quantum computing. And in fact, if you get nothing away but this poster, wanted, get analyzed, Schrodinger's cat, that's enough.
Let's go ahead and do the meeting ending ritual, everybody. 起立，面向佛堂，持架三鞠躬，一鞠躬，再鞠躬，三鞠躬，持架规格是一鞠躬，接班一鞠躬。Okay, everybody, we are done.
Participate in the Tao meeting by joining us online. For information, go to taoism.net/Tao